Welcome to Understand Chemistry. This is Dr. Bilal. In this video, I will talk about molecular weight or molar mass and molar mass distribution of polymers. Molar mass is defined as the mass of 1 mole of a substance and is usually expressed in grams per mole. Small molecules such as ethylene, propylene, vinyl chloride, benzene, and styrene have precise structure, therefore they have precise molar mass. The molar mass of these molecules are shown here, which is 28, 42, 62, 78 and 104 gram per mole for ethylene, propylene, vinyl chloride, benzene and styrene respectively. But this is different in case of polymers. Polymers are composed of chains that may vary in number of monomer units, the extent and frequency of branching, the distribution and length of branching. This means polymers do not have a precise structure or molar mass. Instead, their molar mass is described using several statistically determined averages. These are number average molar mass, weight average molar mass, Z average molar mass, and viscosity average molar mass. Each type of molar mass has its own significance. Let us see first what is number average molar mass. Number average molar mass gives us an idea of average size of polymer chain. In a polymer sample, there are several polymer chains of different sizes. But number average molar mass gives equal weight to all polymer chains. It is more sensitive to small polymer chains. Mn is obtained by dividing the total mass of the sample by the total number of polymer chains. Let me show you how to calculate number average molar mass. In a polymer sample, we have several chains of different lengths. If N1, N2, N3 and so on are the number of chains in the sample, the total number of all types of chain in the sample is given by summation Ni. Now, if M1, M2, M3 and so on are the molar mass of each type of chain, then by multiplying number of one type of chain with the individual mass of chain, we get total mass of one type of chains. The total mass of all type of chain will be obtained by adding product N1 M1, N2 M2, N3 M3 species, which will be equal to summation Ni Mi. From this, we can calculate number average molar mass by dividing total mass of all chains divided by total number of chains. So Mn is equal to summation Ni Mi divided by summation Ni. Let us understand how this formula works. Consider a polymer sample contain the following fraction of polymer chains. So following the formula, by placing the value of all chain and all molar masses, and by computing, we reach to Mn equal to 30,000 gram per mole. Now the question is how to measure Mn practically. Actually, number average molar mass can be measured by any technique that counts the molecules. This means number average molar mass can be measured with the help of colligative property. These are the properties that depend on the number of particles and not on the number of moles. These are vapor pressure osmometry, freezing point depression, boiling point elevation, and osmotic pressure. The other way of measuring Mn is by end group analysis. End group analysis involves identifying and quantifying the functional groups present at the ends of polymer chain. This information helps in determining the number average molar mass by calculating the number of end groups relative to total polymer mass. Here are some common methods for end group analysis. The first one is chemical titration. This method involves reacting the end groups with a titrant and measuring the amount of titrant consumed. It is practically useful for polymers with acidic or basic end groups. The second method is NMR spectroscopy. This is widely used method for determining the number average molar mass. Nuclear magnetic resonance spectroscopy is a powerful technique for identifying the chemical structure of polymer end groups. By analyzing the NMR spectra, you can quantify the N group and calculate the number average molar mass. Both proton NMR and carbon-13 NMR spectroscopy are commonly used. The third technique to calculate the number average molar mass is mass spectrometry. The matrix-assisted laser desorption ionization mass spectrometry, or MALDI-MS, can be used to analyze the molecular weight distribution of polymer and identify N groups, providing information for calculating the number average molar mass. Gel permeation chromatography or size exclusion chromatography is a widely used technique to determine the molar mass distribution of polymers. It separates polymer molecules based on their size in solution. The number average molar mass can be calculated from the resulting molecular weight distribution. Now, let us talk about weight average molar mass. Unlike the number average molar mass, which gives equal weight to each polymer molecule, regardless of its size, the weight average molar mass places greater emphasis on the larger molecules. Now let us see how to calculate weight average molar mass. If M1, M2, M3 is mass of individual polymer chain, and N1, N2, N3 and so on are the number of molecules of each type of polymer chain, then the molar mass of each type of polymer chain is equal to number of chains into molar mass. Then the molar mass of each type of polymer chain is the product of number of chain and the molar mass. In the next step, let us calculate mass of each type of polymer chain multiplied by molar mass of individual chain, which is equal to Ni into Mi, or Ni into Mi square. Now sum up the product Ni into Mi square for all polymer chains, which is equal to summation Ni into Mi square. Now dividing this summation of product of number of all polymer chains and square of molar mass of all the chain with the sum of molar mass of all the chain, we reach to the weight average molar mass. Mathematically, it is written as shown here. The Mi squared is actually gives disproportionate weight to larger chain, since mass or weight of polymer in grams is equal to number of chains into molar mass of chains. By placing this into last expression, the MW will take the form as shown here. Let us see how to use this formula to calculate MW. The data shown in the table is same as we used for number average molar mass calculation. Here is the formula for weight average molar mass. By placing the value of all chain and all molar masses, and by computing, we reach to MW value equal to 33,333.33 gram per mole, which shows that weight average molar mass is greater than number average molar mass. The key reason lies in the mathematical weighing to larger chain. In MW, the molar mass of each chain is squared, which give disproportionate weight to larger chain, whereas in Mn, all chain contribute equally regardless of their size. Guess, in what case MW is equal to Mn? In case of monodisperse polymer, where all the chains are of same size, the MW will be equal to Mn. The term monodisperse has been updated by IUPAC to the more precise term uniform. Now let us see how to measure MW practically. Actually, weight average molar mass is determined by any experiment in which each molecule or chain makes a contribution to the measured result relative to its size. The first one in my list is gel permeation chromatography, also known as a size exclusion chromatography. This technique separates polymer chain based on the size and provide a distribution profile that is used to calculate MW. The second method to find weight average molar mass is light scattering. Static light scattering measured the scattering of light by polymer solution to determine molar mass and size distribution. Viscometry is another way of finding MW. It measures the intrinsic viscosity of polymer solution and relates it to the molar mass. In ultracentrifugation, high-speed centrifugation is used to separate polymer molecules based on their size and density, allowing for the determination of molar mass. This graph represents the molar mass distribution of polymer sample, with the x-axis showing molar mass and the y-axis showing the number of chains at each molar mass. The 2 points marked on the curve are the number average molar mass and the weight average molar mass. Let us see how molar mass averages help to calculate degree of polymerization. The degree of polymerization is defined as the number of monomer units in a polymer chain. We can calculate degree of polymerization by dividing the total mass of polymer to the mass of monomer. As we know, there are several statistically defined molar mass averages for the polymer. Then, which molar mass average should we use to calculate degree of polymerization? The answer is simply the number average molar mass. Mathematically, degree of polymerization is equal to Mn over mass of monomer. Now the question is why Mn is used for calculation of degree of polymerization. This is because number average molar mass equally weights each polymer chain, reflecting the true average number of monomer units per chain. Now the question is why not other molar mass averages are used to calculate degree of polymerization. MW is more sensitive to larger chains and does not directly reflect the number of monomer units. Using MW would overestimate the degree of polymerization because it gives more weight to longer chains. The Z average molar mass is even more sensitive to larger chains and is not suitable for calculating degree of polymerization. The viscosity average molar mass is related to polymer viscosity and is not directly tied to the number of monomer units. Let us see how the molar mass averages help in finding polydispersity index of polymer. The term polydispersity index has been updated by IUPAC to the simpler and more precise term dispersity, now represented by symbol D stroke. Dispersity describes heterogeneity in the polymer sample, means it describes how polymer chain vary in molecular weight or size. In a polymer sample, not all chains are the same length or weight. Some chains are very short, some are very long, and many fall somewhere in between. This variability is what we call heterogeneity, and dispersity quantifies it. Mathematically, dispersity is the ratio of weight average molar mass to number average molar mass. A dispersity of 1 corresponds to completely uniform polymer, where all polymer chains have the same molecular weight. This is known as monodispersed polymer or uniform, which is rarely observed in practice. Processes like living polymerization may approach this ideal. When dispersity is greater than 1, the polymer is considered polydispersed, meaning the polymer chain have a varying molecular weight. This variability arises due to uncontrolled or partially controlled polymerization processes, such as free radical polymerization. A higher dispersity indicates a broader molecular weight distribution. This means the sample contains chains that are both very short and very long, alongside chains of intermediate lengths. In the graph, we see the molar mass distribution of two polymer samples. Sample 1 is represented by the red curve and sample 2 shown by the black curve. Both samples have the same number average molar mass, which means the average chain size calculated equally across all polymer chains is identical in both cases. However, they have different dispersities. Sample 1 has a narrow distribution, meaning most chains are similar in size, leading to easier processing, high mechanical strength, and higher crystallinity. These properties are critical for application requiring uniformity such as high-strength materials. Sample 2 has a broader distribution indicating greater variation in chain size. This makes processing more difficult and result in low mechanical strength and crystallinity. Broad distribution can, however, be useful in bulk applications like adhesives or packaging, where chain variability can enhance flexibility. Let us talk about polymerization processes and how they affect the uniformity of polymer chain. In living polymerization, dispersity ranges from 1.0 to 1.2, which is extremely low. This means almost all the chains have the same molar mass, making them highly uniform. The distribution follows a Poisson pattern, showing that polymer growth is highly controlled and produces precise chain length. In radical polymerization, the dispersity is broader, ranging from 1.2 to 2.5. This reflects the random nature of chain termination. The distribution type is labeled as most probable, meaning there is a peak at the most frequent chain length, but significant variability exists. Polycondensation is a stepwise reaction where monomers form polymers, releasing small molecules like water and methanol. In polycondensation processes, the dispersity ranges from 1.8 to 2.0, which indicates variability in polymer chain length. The Schultz-Flory distribution explains the molecular weight distribution resulting from polycondensation. Now let us talk about Z-average molar mass. The Z-average molar mass is particularly sensitive to high molar mass chains, making it critical for understanding the behavior of polymer with a wide range of molecular weight. The formula of a Z-average molar mass is shown here, where Ni is the number of chains at a particular molar mass Mi. In this example, the table lists molar mass Mi and number of chains Ni. By substituting these values into the formula, we calculate Mz, which in this case comes out to 36,300 gram per mole. This demonstrates how Mz gives greater weight to the higher molecular weight in the sample. Looking at the graph, we see a comparison of different average molar masses. We notice that Mz is greater than Mw, which is greater than Mn, with Mz being the most influenced by larger chains. Understanding Mz is a crucial for characterizing polymer, especially in cases where high molecular weight chains significantly impact material properties like strength and viscosity. Hope you liked the video. Thanks for watching.